So we've seen how we can use direct substitution for polynomial and rational functions, except that in the case of a rational function, the denominator can't be 0. So when the denominator is 0, it's undefined, and but we can still find the limit sometimes. Not always, but sometimes we can find the limit if we do a little bit of algebra. So here in this video, this is the last example, but there's really 4 problems here. So I'm just going to go through these. It might be a little long. All right. So here in this first example, example 6a, all right, we've got a polynomial over a polynomial. So we have a rational function, but if we tried to put in -2, the denominator would be 0. So let's do this. Let's factor this. Now, the one thing that's easy for students to get lazy about is to carry along this limit. Oh, shoot. Okay. Let's see if this works. -2. Okay. So we have to carry along this limit. All right, but we're going to factor the numerator here. So I can see that I can factor out an x. Let me just do that up here. X squared minus x minus 6. Okay. And so then I can factor that quadratic, and I'll end up with x times x minus 3 times x plus 2, right? When I factor that. And then I can factor the denominator as well. And I'll have x times x plus 2, right? All right. Now, you can see that we have a factor of x plus 2 in the numerator and the denominator. And as long as we're not going directly to 2, or to, sorry, -2, then we can cancel those. And we're not. We're doing the limit, right? So we're not going directly to -2. We're going to sneak up on it. So we're never going to put in -2. So we're just going to cancel that, and we can also cancel the x too, as long as we're not going to 0, right? And then we're not. We're trying to get to -2, so we can also cancel the x's. So what do we have left? All right, near x equals -2, as long as we don't go to -2 directly, then the function looks like x minus 3, right? It's just the limit at x approaches -2 of x minus 3. And now that we can do direct substitution, and we get a -5. So even though the value of what's going on here? Even though the value of this function is undefined at -2, in the limit, it looks like it's approaching -5. Essentially, we have a hole in the function at x equals -2. Okay? All right, so let's go to the next one. Again, we just have to do some algebra here. And I think what I want to do is expand that square and see if I can find some things that cancel, right? So let's just rewrite this. This is the limit as x approaches 0 let's expand this square. We get x squared minus 4x plus 4, and then minus 4. Oh, all right, like that. And then this is all over x. Okay, now we can see that we have a +4 and a -4. Those cancel out. And then we have, again, carry the limit along. X approaches 0. And we have x squared minus 4x. So I'm going to factor out an x, and I'll get x times x minus 4 all over x. And now you can see, as long as we're not going directly to 0, then we can cancel these x's, okay? Because we're not going to go directly to 0. We're going to sneak up on it. So everywhere else, the function looks like x minus 4. Okay, and now we can do direct substitution, and we'll get a -4. All right, that's all there is to it. It's just some algebra. And that's a little simplification. All right, so let's keep going here. It's the same sort of thing. We just have to simplify this until we can figure out what's going on. All right, so you can see again, if I try to do direct substitution, I get a 0 in the denominator. Here I have the difference of two rational functions. So what do I need to do? Well, I can see, whenever I subtract fractions, I need a common denominator. So let's first of all factor the second denominator. All right, so we can see what we're dealing with here. So we have 1 over x minus 2 over x times x plus 2, right? All right, so I need a factor of x plus 2 in the first fraction so that I can combine these two fractions into one. That's what I think I need to do. So again, I'm carrying along the limit and I'm going to multiply 1 over x times x plus 2 over x plus 2. All right, because x plus 2 over x plus 2 is just 1. And so what I'll end up with is x plus 2 over x times x plus 2. And then I can, now it has the same denominator as, okay, hang on, as this other one. Golly, jeepers, x plus 2. Okay, now I have the same denominator, and isn't that convenient because I have x plus 2 minus 2. So this is equal to the limit as x approaches 0. I have x plus 2 minus 2, which is just x, over x times x plus 2. All right. Now, I can see as long as x is not 0, then I can cancel these x's, right? Okay, and we're not going directly to 0. We're sneaking up on it. So everywhere else, it looks like, let's see, I write it over here. Limit as x approaches 0 of 1 over x plus 2. All right? So now I can just do direct substitution and I just get 1/2. So that's my limit. As x approaches 0, this function approaches 1/2. All right? So remember, it's undefined at 0. There's a hole in the function at 0, but as I approach 0, the value of this function approaches 1/2. All right, we got one more thing here. And here you can see we have a square root. All right, now there's a little trick with square roots. And what we want to do is multiply by the conjugate of the numerator. Okay, now this relies on the fact that if you have the difference of two squares, right, I'll just write it down here. If we have a squared minus b squared, that factors into a plus b times a minus b. Okay, these a plus b and a minus b are conjugates of each other. They're called conjugates. All right, so and you notice when we do that, we multiply those binomials. Usually we get a middle term, but notice the middle term goes away because we have an a times b and a minus a times b, and then so the middle term goes away, and we just end up with a squared minus b squared. Okay, so what I'm going to do here, this is a trick you need to know how to do. I'm going to multiply this by 1, but the 1 is going to be the square root of x plus, what the heck? Square root of x plus 2 over the square root of x plus 2. So notice the square root of x plus 2 is the conjugate of the square root of x minus 2. So when we multiply those together, we get the difference of two squares. All right. So and square root of x plus 2 over the square root of x plus 2 is just 1, right? All right, so let's rewrite this. We're going to write the limit as x approaches 4. And when I multiply the numerators, I'm going to get x minus 4. It's the square of the square root of x minus the square of 2. Okay, right? It's the difference of two squares. That's how I got that. And notice, isn't that convenient? We have an x minus 4 in the denominator, and then all of that is times the square root of x plus 2. Square root of x plus 2. All right? So, everywhere but 4, when x equals 4, I can't, this doesn't exist. But everywhere else, as long as x is not 4, I can cancel those factors of x minus 4. And so what I have left is the limit as x approaches 4 of 4, x minus, what am I doing? Hang on. We canceled everything in the numerator, so we're left with a 1. And then we have a square root of x plus 2. All right. Now we can just do direct substitution, and we're going to get 1 over, square root of 4 is 2, 2 plus 2. 2 plus 2 is 4. So our answer is 1/4. That limit goes to 1/4, okay? So remember that trick of multiplying by the conjugate, and that allows us to get rid of that square root in the numerator, and conveniently, it ends up being a factor in the denominator, so we can cancel it. All right, so watch for that trick. All right, that's all the examples I have for you, and I'll meet you in class.